Welcome back to Talk Tensors. Today, we're going to be taking a deep dive into this paper called Improving the Performance of Echo-State Networks Through State Feedback.
Oh, this is a fun one.
Yeah, it looks pretty interesting.
Yeah, and it has some really clever ideas about making echo-state networks, ESNs, even more efficient.
And we'll hear a lot about ESNs these days, especially when we're dealing with time series data.
Right, like stock prices, weather patterns.
Exactly, all that good stuff.
Yeah, and they're generally a bit easier on your computer than some other methods, but this paper kind of takes it a step further.
Okay, so let's break this down for our listeners who might not be super familiar with ESNs.
Sure.
What is it at the core of this idea that makes this paper so interesting?
So imagine you have an ESN, right? And it's doing a pretty good job.
Okay.
This paper proposes taking some of the ESN's output and feeding it back into its own input.
Okay.
It's like giving the network a little boost of self-awareness, letting it learn from its own predictions.
So instead of just processing new data, it gets to consider its own previous thoughts, so to speak.
Exactly.
I could see how that might lead to more accurate predictions.
Exactly. It's a really clever way to add more flexibility without making the network more complex.
Okay.
And the implications are pretty significant. Essentially, you can get the same level of accuracy as a much larger network, but with way less computational overhead.
That sounds really promising, especially when you're dealing with complex time series data where computation can be a real bottleneck.
Yeah, for sure.
Could you give us a quick refresher on how a typical ESN works before we get into the nitty-gritty?
Yeah, definitely. So an ESN is kind of like a black box with two main parts. First, you've got the reservoir.
Okay.
Think of it as a memory bank that captures patterns in the data over time.
Gotcha.
The cool thing about the reservoir is that its connections are fixed, meaning they don't change during training.
Okay.
And then you have the output layer,
Right.
which learns how to interpret the information that's stored in the reservoir to make predictions.
So the reservoir is doing the heavy lifting of analyzing the time series, and the output layer is figuring out what it all means.
That's a great way to put it. And because that reservoir structure is fixed training, an ESN is much simpler and computationally cheaper compared to other types of neural networks.
Makes sense.
But as you might imagine, this fixed structure can also limit the ESN's ability to solve certain complex problems.
Right.
It's like trying to run a marathon with only one type of stride.
Yeah.
You might finish, but you're not going to win.
That makes sense.
So that's where this feedback mechanism comes in.
Okay, so is it like adjusting that stride mid-race to be more efficient?
Exactly. The paper proposes adding a feedback term to the ESN's input, which takes a portion of its current thoughts and feeds them back into the system. It's like the ESN is constantly reflecting on its own performance and adjusting its approach.
Okay, so how does this feedback actually work in practice?
It all comes down to tweaking the way the reservoir processes information. You see, the reservoir structure is defined by a matrix.
Okay.
Let's call it A.
Okay.
Which dictates how information flows within the reservoir.
Right.
In a traditional ESN, this A matrix is randomly generated and it remains fixed.
Okay.
And we only train the output weights, how the network interprets the information coming from the reservoir.
Gotcha.
So with this new feedback idea, are we actually changing the A matrix itself?
Yeah, that's what I was wondering.
Not directly. We're keeping the A matrix fixed, but we're adding a new element to the equation.
Okay.
The feedback loop takes the ESN's current state, which is represented by a vector, let's call it xk, and multiplies it by a set of feedback weights, v vector. This product is then added to the ESN's input, subtly modifying how the information flows through that fixed reservoir.
So it sounds like we're not messing with the ESN's core structure, but we're kind of giving it this new tool to work with. Almost like adding a new dimension to its thinking process, would you say?
That's a great way to think about it. The feedback loop is essentially a way to manipulate the dynamics of the reservoir without directly changing its fundamental structure.
Okay, I get that. But I imagine there's got to be a catch, right?
Yeah.
How do we find the best values for those feedback weights?
Right.
The V vector.
Yeah.
That seems like a whole other challenge.
You're absolutely right. That's where things get a bit more complex.
Okay.
The authors use a technique called gradient descent to optimize the V vector.
Okay.
It's essentially a trial and error process where we try different values for V and see how they impact the ESN's performance.
Okay.
The goal is to find the values that minimize the difference between the ESN's predictions and the actual data.
Gotcha. So it's like we're fine-tuning the ESN's self-awareness to make its predictions as accurate as possible.
Exactly.
Okay.
But finding the best v-vector isn't always straightforward. The authors point out that this optimization process can get stuck in what we call local minima.
Yeah.
Imagine you're trying to find the lowest point in a valley, but there are all these little dips and bumps that can mislead you.
Right. It's not as easy as it sounds.
Yeah.
So it's not just a matter of blindly applying gradient descent.
Right.
We need to be a bit more strategic.
Exactly. And the authors have some clever tricks up their sleeve to address that challenge, which we'll dive into later.
All right.
But first, I think it's time to see how well this feedback mechanism actually works in practice.
Let's see it. I want to see if it lives up to the hype.
Okay, the authors put their feedback enhanced ESNs to the test on 3 very different tasks to demonstrate the power of their method.
Right.
Let's start with the first one. The chaotic Mackey glass system.
Mackey glass. That sounds familiar. I remember that from my chaos theory days.
Yeah.
It's known for its unpredictable behavior, right?
It is. It's a classic benchmark for testing how well a system can model complex dynamics. The researchers used it to compare the performance of traditional ESNs to those enhanced with feedback, and the results were pretty impressive.
So did the feedback mechanism actually make a difference?
It did. The feedback-enhanced ESNs consistently outperformed traditional ESNs with the same number of nodes.
Oh, okay.
In fact, they achieved similar levels of accuracy to ESNs that were twice as large.
Wow.
Meaning they were able to achieve the same performance with half the computational cost.
Now that's what I call efficiency. Cutting the computational cost in half while maintaining the same level of accuracy that's remarkable.
Right.
Was that just a one-off fluke? Or did they see these consistent results across multiple tests?
Yeah, they weren't content with just one test. They repeated these simulations with thousands of randomly generated ESNs.
Okay.
And the results were consistent.
Wow.
Adding feedback significantly boosted performance.
That's awesome. So it wasn't just a one-trick pony.
No.
Did they test it on other tasks too?
They did. They didn't stop at the Mackey glass system. Next, they tested their method on a completely different type of problem. Nonlinear channel equalization.
Channel equalization. That sounds a bit more technical.
Yeah.
What does that even involve?
Imagine you're trying to receive a message that's been transmitted through a noisy channel.
Okay.
The signal gets distorted along the way, and your job is to decode it and recover the original message.
So it's like trying to understand someone speaking through a bad phone connection.
Exactly.
You got to filter out the noise to get the clear message.
You got it.
Okay.
And this task is particularly challenging because the distortion is nonlinear.
Okay.
Meaning it's not a simple matter of just amplifying the signal.
Right.
It requires a system that can understand and compensate for complex patterns of distortion.
Okay, so how did the feedback-enhanced ESNs fare in this challenging task?
They did exceptionally well. They achieved significantly lower error rates.
Wow.
Compared to traditional ESNs. And here's the kicker. They often needed far fewer nodes to achieve the same level of accuracy.
So not just about efficiency, but also about finding the best possible solution.
Right.
This feedback mechanism is really starting to sound like a game changer.
It really is.
Okay.
And to really showcase its versatility,
Right.
the authors also tested it on a third, more real-world task.
Okay, let's hear it.
The coupled electric drives dataset.
Okay.
This dataset focuses on system identification for a complex, noisy system with real-world applications.
So we're moving beyond theoretical examples now and into practical problem solving.
Yeah.
Okay, I'm eager to hear how they did.
Well, this real-world task proved to be no match for the feedback-enhanced ESNs either.
Okay.
They provided a much tighter fit to the data, meaning their predictions were more accurate.
Okay.
And what's really interesting is that the feedback mechanism also helped the ESN capture subtle correlations hidden within the noise.
Oh, wow.
Leading to a deeper understanding of the system's dynamics.
So it's giving us better insights into the data as well. Okay, I'm thoroughly impressed. It sounds like this feedback idea is delivering on its promise.
Yeah.
Making ESNs more efficient, more reliable, and even giving us deeper insights into the data.
You got it.
But before we jump to any conclusions, we should probably also consider the limitations.
Yeah.
I imagine there are some.
There are.
While the authors lay out a solid framework for optimizing those feedback weights, finding the absolute optimal settings can be tricky, especially as the task complexity increases, right?
Exactly. The more complex the terrain, the harder it is to find that perfect setting.
Right. That makes sense.
Yeah. And they even hint that more sophisticated optimization algorithms might be needed to really unlock the full potential of this feedback mechanism.
Yeah.
But even with those limitations, the results speak for themselves. Adding feedback is a powerful way to boost the performance of ESNs.
Absolutely. This has been a truly fascinating deep dive so far. We've covered a lot.
Yeah.
From the basics of ESNs to this game-changing feedback idea and its impressive results across these diverse tasks. But we've only scratched the surface.
Right.
There's still so much more to explore.
For sure.
In the next part of our deep dive, we'll delve into the historical roots of this feedback concept.
Okay.
And examine how this research builds upon previous work in the field.
Sounds good.
So stay tuned, and we'll be back soon to continue our exploration of this groundbreaking paper right here on Talk Tensors.
Looking forward to it. Welcome back to Talk Tensors.
All right, so last time we left off with this amazing idea of using feedback to supercharge echo-state networks, or ESNs.
Yeah.
We saw some pretty impressive results, basically getting the performance of a bigger network with a smaller, more efficient one.
Right, and you know what's really elegant about this approach is how it builds upon those fundamental principles of ESNs. Remember, one of the key advantages of ESNs is their fixed internal structure.
Right.
That reservoir that captures temporal patterns. It's what makes them computationally lighter than traditional recurrent neural networks.
Right, because you don't have to train all those internal connections. You just focus on optimizing those output weights.
Right.
But as we discussed, this fixed structure can also be a bit of a double-edged sword.
Exactly. It simplifies training,
Right.
but it can limit the ESN's flexibility.
Right.
So the brilliance of this feedback idea is that it lets you manipulate the dynamics of that reservoir without actually changing its structure.
Okay.
It's like adding a new dimension of control without messing with the underlying hardware.
Okay, so I'm getting the why this is important.
Okay.
But I still kind of want to dig a little deeper into the how did this idea even come about? Was it a sudden aha moment, or did it evolve from earlier research?
Well, it's always tricky to pinpoint the exact origin of an idea, but this particular paper definitely benefits from this rich history of research in both reservoir computing and neural networks. In fact, the concept of feedback has been explored in various forms before.
Really? Could you give us some examples?
Yeah, well, for instance, there's a concept called teacher forcing, which has been used in training recurrent neural networks. It involves feeding the network the correct output sequence during training to guide its learning process.
So it's kind of like giving the network training wheels?
Yeah, kind of like that.
Interesting. But how is that connected to the feedback we're talking about in ESNs?
Well, both techniques involve using this extra information to guide the network.
Okay.
But with teacher forcing, you're giving the network the answers during training.
Right.
Whereas in this ESN feedback, you're using the network's own output as an additional input signal.
Okay, so it's more about guiding the network toward better performance rather than explicitly telling it the right answer.
Exactly. It's more about subtly nudging it in the right direction.
Okay.
Letting it learn from its own attempts.
Got it. And another related concept, I think I've heard this before, is closed-loop feedback control.
Yes.
This has been used in engineering to stabilize and regulate systems.
Right, exactly like a thermostat.
Right.
Adjusting the temperature based on the current room reading.
So this ESN feedback is kind of like building a little thermostat into the network itself.
That's a great analogy.
It's constantly monitoring its own performance and adjusting accordingly.
Exactly. And, you know, this connection to control theory actually highlights another fascinating aspect of this feedback mechanism.
What's that?
It emphasizes the idea of using feedback to not just improve accuracy, but also to control and shape the ESN's behavior more broadly.
So it has implications beyond just performance optimization then.
Exactly.
You could use feedback to make ESNs more robust to noise or even customize them for specific tasks.
Exactly. And the possibilities are pretty exciting.
Wow.
Now, in the context of ESN research specifically, there have been some previous attempts to incorporate feedback.
Okay.
For instance, one study explored the idea of adding a second auxiliary ESN that receives feedback from the main ESN and then feeds its output back into the main network.
So it's like having two ESNs talking to each other, trying to figure things out.
In a way, yes. However, this approach involves training these additional connections between the two networks, adding to the complexity. The beauty of the method proposed in this paper is its simplicity.
Okay.
It achieves feedback with very minimal modifications to the ESN architecture.
Elegant and effective.
Indeed. And, this paper also does a great job of addressing some potential concerns about incorporating feedback.
Okay.
Remember, we talked about the importance of maintaining stability in the ESN.
Right. We don't want those feedback loops to send the network into a frenzy.
Exactly. So the authors have actually developed a specific method for constraining those feedback weights to ensure stability during the optimization process.
Okay.
They basically make sure that the feedback doesn't amplify any unwanted oscillations or instabilities within the network.
That makes sense. It's like making sure the thermostat doesn't accidentally turn the heater into a furnace.
Another perfect analogy. And, this careful attention to detail really sets this paper apart. They've not only come up with this innovative idea, but they've also thought through the practical considerations of implementing it.
Okay, so I think we've done a pretty good job of understanding the background and motivations behind this feedback idea.
Yeah.
Now, I want to shift gears a bit and talk about its potential impact.
Okay.
We've seen some amazing results in these benchmark tasks.
Right.
But what about the bigger picture? How could this feedback technique change the way we use and think about ESNs in the real world?
That's the million-dollar question, isn't it?
Yeah.
And honestly, it's still a bit early to say for sure what the long-term impact will be.
Right.
But based on the results we've seen, I think it's safe to say that this has the potential to be a real game changer.
Give us some concrete examples. How could this impact different fields?
Well, think about fields like robotics, where computational efficiency is crucial.
Okay.
Imagine being able to control a robot's movements with a much smaller, faster ESN, thanks to this feedback mechanism. It could lead to more agile and responsive robots.
Oh, that's a good one. And what about something like financial modeling?
Absolutely, and finance time is money, literally. So being able to train ESNs faster and with less computational overhead could be a huge advantage. Traders could get quicker and more accurate predictions, potentially giving them an edge in the market.
So faster, more efficient, and potentially even more profitable.
Exactly.
Now, that's a headline I'd like to read.
Right, and this is just scratching the surface.
Wow.
We could also see applications in areas like healthcare, where ESNs are already being used for things like predicting patient outcomes or analyzing medical time series data.
It's fascinating to think that this seemingly simple tweak could have such a ripple effect across so many fields.
It really is. And, beyond the specific applications, I think this paper also has this broader message for the machine learning community.
What's that?
It's a reminder that even in a field that's rapidly evolving, it's important to step back and reconsider the fundamentals.
You mean sometimes the biggest breakthroughs come from revisiting the basics and asking what if?
Exactly. And who knows, maybe this feedback idea is just the tip of the iceberg. Perhaps there are other hidden gems within ESNs or even other machine learning techniques just waiting to be unearthed.
So what you're saying is there's a whole lot of potential for innovation and discovery in this space.
Absolutely. And this paper is just this fantastic reminder that even the simplest ideas can have a profound impact.
Well, on that note, I think it's time for us to take a quick break.
Okay.
We've covered a lot of ground, from the historical roots of feedback to its potential impact on the future of ESNs.
It's been a fascinating conversation, but our exploration isn't over yet.
Right.
We still have to tackle a crucial aspect of this paper that we haven't touched upon yet.
Okay.
The novel notions section, where the authors outline some thought-provoking extensions of their work.
Ah, yes, the what if section.
Exactly.
I'm always eager to hear where researchers think their work could lead.
Right.
So stay tuned, and we'll be back with you shortly to dive into those exciting possibilities right here on Talk Tensors.
Sounds good.
Welcome back to Talk Tensors. Over the last 2 segments, we've been exploring this really cool paper about making echo state networks, or ESNs, even better using this feedback mechanism. We've seen how it works, why it's important, and even got a glimpse of its potential impact on all kinds of different fields.
It's been a fascinating journey so far.
Absolutely. But now I'm really curious about where this research might lead in the future.
Okay.
We briefly touched on the novel notions section of the paper, where the authors kind of hint at some exciting extensions of their work. So are you ready to put on our speculative hats and dive into those possibilities?
I'm always up for a bit of speculation. Let's see what they have in store for us.
All right, so what kind of ideas are they proposing?
Well, one of the most exciting directions they point to is exploring more sophisticated optimization algorithms to fine-tune those feedback weights.
Okay.
Remember how we talked about finding the best values for that V's vector?
Yeah.
And how that process can sometimes get stuck in those tricky local minima.
All right, it's like trying to find the lowest point in a valley, but the terrain is full of deceptive dips and bumps.
Exactly. So the author suggests that instead of just relying solely on gradient descent,
Okay.
we could explore some more powerful algorithms like evolutionary algorithms or swarm intelligence.
Okay.
These techniques are specifically designed to kind of navigate those complex search spaces more effectively and avoid getting trapped in those local minima.
So it's like upgrading our search party from a group of casual hikers to a team of expert mountaineers,
That's a fantastic analogy.
equipped with all the best tools and techniques.
Exactly. And I think this could open up a whole new avenue for research. Imagine developing these optimization algorithms specifically tailored for ESNs with feedback.
Okay.
Algorithms that can find those optimal V vector values more efficiently and reliably.
It's amazing to think that this feedback mechanism could be the catalyst for this whole new wave of research and optimization.
Absolutely. And the potential benefits go beyond just finding better feedback settings. These advanced algorithms could also help us design more complex ESN architectures, perhaps even networks of interconnected ESNs, each with its own feedback loop,
Wow.
working together to solve even more challenging problems.
Wait, multiple ESNs interacting with each other?
Yeah.
That sounds incredibly complex.
It is, but it's really cool. Imagine you have this network of ESNs,
Okay.
each specialized for a specific aspect of a larger task. They could communicate with each other through these feedback loops,
Okay.
sharing information and refining their predictions collaboratively.
So it's like having a team of experts, each with their unique skills and knowledge, working together to solve a complex puzzle.
Exactly. And I think this could lead to ESNs capable of tackling problems of unprecedented complexity.
That's incredible. But I imagine there are also some challenges involved in training and managing such interconnected networks.
You're right, it's not without its hurdles.
Right.
Training and optimizing these networks would require new approaches and algorithms that can kind of handle that increased complexity and the interdependencies.
Yeah.
But the authors suggest that techniques from distributed optimization and parallel computing could offer some potential solutions.
So instead of relying on one supercomputer to handle the entire workload, we could have a team of smaller computers working together, sharing the burden.
Right.
And communicating efficiently.
Exactly. And with the advancements in cloud computing and parallel processing, this type of distributed approach is becoming more and more feasible.
Right.
Who knows? We might even see specialized hardware designed specifically for these interconnected ESN architectures in the future.
It's pretty mind-blowing, but I have a feeling the authors have even more novel notions up their sleeves.
They do.
What else caught your eye?
Well, one that I found particularly intriguing was the idea of using feedback to explore and exploit the chaotic dynamics that can arise in ESNs.
Chaos. Isn't that something we usually try to avoid in machine learning?
You would think so, right?
Yeah.
But chaos can actually be a source of immense computational power. Think of the human brain. It's a highly complex system with chaotic elements, and yet it's capable of these extraordinary feats of intelligence and creativity.
So instead of trying to eliminate chaos in ESNs, we could actually learn to harness it.
Precisely. The authors propose that by carefully tuning those feedback weights, we might be able to nudge the ESN into specific chaotic regimes where its computational capabilities are maximized.
This sounds like we're not just building machines, we're trying to unlock their hidden potential, almost like we're trying to tap into their creative spark.
I love that analogy. It really captures the essence of this idea. And this notion of harnessing chaos in ESNs aligns with this broader trend in machine learning. This move away from purely deterministic systems, and embracing the power of randomness and complexity.
So this research is about more than just making ESNs better. It's about expanding our understanding of what these systems are truly capable of.
Exactly. That's what I find so exciting about this paper. It's not just about these incremental improvements. It's about pushing the boundaries, challenging assumptions, and opening up new avenues for exploration and discovery.
Well, on that inspiring note, I think it's time to wrap up our deep dive into this remarkable paper. We've covered a lot of ground from the technical details of ESNs with feedback to those broader implications for machine learning.
It's been an incredible journey. We've delved into the history of this concept, explored its current applications, and even glimpsed its potential to shape the future of machine learning.
A huge thank you to our listeners for joining us on this adventure. We hope you gained a deeper appreciation for the power and potential of echo-state networks and this ingenious idea of using feedback to kind of unlock their full capabilities.
And remember, the journey of discovery doesn't end here. As this paper demonstrates, there's still so much to explore and understand in the world of machine learning.
That's right. So keep those curious minds engaged. Keep asking those what-if questions, and who knows what groundbreaking discoveries await us in the future. This is Talk Tensors signing off.